top-down parsing strategies build syntax trees efficiently, right up until they hit left recursive grammar. The logic loops endlessly and the structure fails. The alternative is bottom-up parsing, specifically shift-reduce. Instead of building down, it works upward by managing a working stack of symbols and scanning an input buffer. Here, the stack holds an expression and a term, while the input buffer has a multiplication sign and an ID waiting. The shift-reduce parser hits a wall. Should it shift the next token or reduce what is there? It lacks information to decide. In compiler design, ambiguity leads to errors. The system requires a deterministic path to ensure the source code is translated exactly as written. LR parsing solves this. It scans the input from left to right and constructs a rightmost derivation in reverse. Because it builds from the bottom up, it handles left recursive rules without getting stuck in a loop. To eliminate guesswork, an LR parser uses a structural memory. It tracks exactly which parts of a production rule it has already seen and which tokens are valid next steps. This memory is built by breaking grammar rules down into specific stages of progress. We track this progress using an LR0 item. By placing a dot within a production rule, we create a bookmark that shows the parser's current position. As tokens are read, the dot moves from left to right. When the dot is before a symbol, the parser is expecting it. Once the dot moves past it, that symbol has been successfully recognized. Since multiple rules might be relevant at once, the parser groups these items into a state. This represents the total set of possibilities the parser is considering at a specific moment. Moving between these states is handled by the goTo function. If the parser is in state 0 and encounters an ID, the goTo function directs it to state 3. By connecting every state through these transitions, we create a complete map of the grammar. The parser can now navigate any valid sequence of tokens by following these predefined paths. This network is finalized into the action table. This matrix serves as the operational instructions for the parser, cross-referencing the current state with the next input symbol. For every possible combination, the table specifies a single action: shift, reduce, accept, or error. This removes the need for the parser to guess during the shift-reduce process. The method used to fill this table determines the parser's capabilities. Simple LR, or SLR, is easy to construct and results in small tables, but it cannot handle more complex, ambiguous grammars. Canonical LR, or CLR, is the most powerful variant. It uses look-ahead symbols to distinguish between different parsing scenarios, but this leads to a massive increase in the number of states, which consumes significant memory. Look-ahead LAR, or LALR, provides a middle ground. It takes the power of CLR, but merges states that have identical core logic, reducing the table size back to manageable levels. Because LALR provides the predictive power of CLR without the memory overhead, it has become the standard choice for most modern language tools. Manually calculating the states and transitions for a language with hundreds of rules is a significant bottleneck for developers. To solve this, computer scientists developed parser generators. These tools automate the construction of the states and the action table. A developer provides a file defining the grammar rules of the language. This file is fed into a generator like Yacc, or its modern version, Bison. The generator processes the grammar, determines the necessary look-aheads, and produces a complete parser written in C code. This process replaces the initial confusion of shift-reduced conflicts with the mathematical consistency of an LALR table. This level of automation means that once a grammar is defined, the parser can systematically verify the structure of the input, providing a consistent foundation for the remaining phases of the compiler.